mean to start. All right. We learnt that as you move at relativistic speeds, time dilates. Now remember, the way to remember it is a moving clock runs slow, but that can be a bit confusing because if you think about, oh, this is my clock and I'm moving, so it runs slow. It's like, no, the clock is not moving relative to you. It's stationary with you then. It would not run slow. You would observe it running at a normal speed. It's if you saw someone else who had a clock and they were moving relative to you with their clock, you would see their clock run slow. And they would see your clock run slow. And that doesn't make sense, but it happens. And the resolution for how it can work is because while you're both experiencing different times, you're also experiencing different space. And that solves a lot of the crazy conflicts that don't seem like they would work. And the topic of different spaces for relativistic speeds is called length contraction. Now, first thing you need to know is that length contraction is when space is contracted in the direction of relativistic motion. And that's important. It only occurs in the direction. So we've got to get our vector hats on and think in terms of vectors and imagine that some object's velocity has a very specific one-dimensional direction. Okay? Or, I guess, three-dimensional direction, depending on what I mean by that, but anyway. And that direction is the direction in which length will contract along that one-dimensional axis that the vector lies on of its velocity. That's the length that contracts. So if you're running forward, you don't get shorter, basically. If that makes sense. If you're running forward, you don't get shorter. You get thinner. You don't even get thinner this way. If I'm running that way, I don't go that way. I go this way. Okay? You want a little diagram of that? Length becomes contracted in the direction of travel. Why? Why? Because, great question. Don't ask physicists why. We don't know. It just does. We know how we decided this was true. We decided it was true because we observed it, and it has to be the case for the laws of physics to not be broken. Let's look at an example. Here's the formula. This is in your formula and data book. Does that look fairly familiar? It should. I want you all to have a look at your time dilation formula and tell me what is in common and what is different. What do you mean the L0 is not the same? What's different? Right. This here is a special thing. It's called the Lorentz factor. Now you might remember the word Lorentz from when we watched that quick video and that guy had built that board that did, he called them spatial transformations. They were Lorentz transformations, basically multiplying by a factor of the Lorentz factor. And what the Lorentz factor does is introduce the effects of relativity, basically. It gives you a relativistic factor of your lengths. So literally, this formula says relativistic length is proper length times by a factor. And that factor only depends on speed. It's actually pretty simple when you think about it. And it's pretty impressive how clean the mathematics is. I know this might look a bit ugly and messy, but really it's the square root of 1 minus a fraction of the speed of light. That's all it is. If you're going at the speed of light, this becomes 0, and that becomes 0, and there's no change. 1 minus 0 becomes 1, square root of 1 is 1, and there's no change. If this is slightly less than c squared, then you get a fraction, 0.9. And then you only get 0.1 in here, you take the square root of that's even less, and you get a very small fraction of L0. It's actually a very simple piece of mathematics, really, which determines how special relativity works, which is kind of cool. Now, let's just be very clear about what each of those things mean in case it's not clear by default. L is relative length. L0, proper length. And V, of course, is velocity. Honestly, if you don't feel the need to copy those down, if it's kind of obvious, feel free, but you've just been introduced to relative and proper as a term for 2 different lengths or 2 different times, so it's probably worth it, just so that you have it there. Now we need to establish again what the proper length is. So let's be very clear about this, because as we saw with proper time, it can be one of the trickier parts of the problem to determine what is the proper length, okay? I think it's easier for length than it was for time. The proper length is, it's a bit of a long convoluted way of saying you're moving at the same speed as the distance you're trying to measure. You're in the same frame of reference as the distance you're trying to measure. Here we go. A spaceship passes you at a speed of 0.80 c. You measure its length to be 90 meters. Calculate the length it would be to observers on board the spaceship. This is tricky because of this language. This language is common. So let's establish what this means. We've talked before about a train going from point A to point B. And maybe the front of the train hits point A when t equals 0, and the front of the train hits point B when t equals 1 second, right? For you standing on a platform in between point A and B. Okay. We've established that in that case, the person on the train is the person measuring proper time. Because if they had their clock is present at both events. Okay, so their clock would be here when this event happens, they get to point A, and their clock would be here when this event happens, them getting to point B. That's the event that we're measuring the time of. The clock's present at both events, the start and the end of the event. Is that clear? This language here is different. It's essentially the opposite. When we say something passes you, what we mean is you are point A at t equals 0. At t equals 0, the train is in front of you there. And then a second later, at t equals 1, the train has passed you. Who's measuring proper time in that situation? Is the person standing on the train with their clock, is their clock present at both events? Right, so 2 different situations, and they're a bit weird, but they're the opposite. So you, standing still, are measuring the time of the train passing you. The events that happen is the train reaches you, the train passes you. You are present at both events and could measure that time with one clock. So in that context, you would measure proper time. In the other context, where we say a train goes through a platform or through a tunnel, we're talking about the train entering the tunnel and exiting the tunnel. There is 2 different sort of positions, and only someone on board the train there for both events at both places can measure the proper time. When they use this language of passing you, they mean something different. And that comes up a lot and can be really confusing and make you doubt what true time and proper time and all that is. So hopefully that little explanation will help us. Now, let's apply it here for a length contraction problem. The proper length is the length that can be measured by a person who sees the start and end points not moving relative to them, okay? If we're talking about a train passing you, who measures length? If the train passes you, who measures the length that is stationary relative to them? If you're standing there on the platform and the train's here, can you measure the length with the start and end points of what you're measuring not moving relative to you? No, the start and end points are moving past you. So relative to you, the length you're trying to measure is moving. So you measure relative length. The person on the train could look at the front of the train and the back of the train, and to them it would look like they weren't moving, and they could measure the length and it would be proper length. Is that okay? All right. So is this distance here, 90 meters, relative length or proper length? You measure it, the spaceship is passing you, you're measuring a relative length. L equals 90 meters. And let's use the notation they've given for significant figures, 9.0 by 10 meters. Now recall that L equals L0 times by the Lorentz factor, square root of 1 minus v squared on c. Our velocity is 0.80 c, very kindly given to us as a fraction of the speed of light, which makes things easy. You guys will remember. That means that that will cancel. Let's sub in our numbers and solve. We've got 9.0 by 10 equals, that's how I wrote it. We could just do it as 90. Easier math, yep, sure. 90 equals L0 times by the Lorentz factor. 1 minus our c is going to get squared. This c, when we sub this in to here, the c is going to become c squared and it will cancel top and bottom. So we're just left with 0.8 squared. Is everyone okay with that maths, or do you want me to lay that out? Happy to lay it out if you'd like to see it. We can see that we're not going to solve for L0 here, so we need to rearrange this formula by dividing both sides by the square root of 1 minus 0.8 squared. Let's do that. We do it for both sides, square root 1 minus 0.8 squared. Okay. We end up with L0 equals 90 divided by square root of, that'll be 0.64, so square root of 0.36. All right? Square root of 0.36. Is 0.6. 90 divided by 0.6, 150. So who would measure the train to be 150 meters? The person on the train, and hence the person on the platform sees a moving object contracted in the direction it is moving. Literally, they would measure all of it, everything on board, the person themselves as well, as being shorter. Now, weirdly, this does not mean that the person has their organs compressed and dies, because for them they're perfectly fine. It's almost like an optical illusion, but it is real. It does really happen. For whatever that means. We'll leave that to the philosophers, but... Any questions about that one? You need me to go back, or are you good? Nope. All right. This is a big problem. Let's just go through it quickly. If you don't want to copy notes on this, it's fine. It's a very long sort of example. But I do think it's worth discussing because it brings up a lot of those proper length, proper time sort of questions, okay? So, a certain star is 36 light years away. Calculate how many years would it take a spacecraft traveling at 0.98 c to reach that star from Earth as measured by an observer on Earth. Okay. We want to know how long it would take someone to travel 36 light years if they were on Earth. How do we do it? It's a distance. Yeah. It's just some distance. What do we reckon? What are some first steps? Again, I don't need you to copy this example down. I want us to brainstorm this and work through this together, and I want you guys to help me out. I like the idea of drawing it, so let's draw a quick diagram. This is Earth. This is, what's a good star, Alex? Rigel? Is Rigel 36 light years away? 36 LY for light years. Now, this is a length. Who has measured that length? Someone who? Right, so what length is that? Is that relative length or is that a proper length? 36 light years. When we look up at a star and we measure the length of that star from Earth, is that relative length or proper length? Guys, join us. What did we say? Hands up if you think it's relative length. You're measuring the length of a moving thing relative to you. Hands up if you think it's proper length. You're stationary next to the thing you're measuring. It is a bit confusing. We have to actually assume that the star is in the same reference frame as Earth for this to work, which, considering the large distances, even if they're sort of orbiting their stars differently and this star is orbiting a black hole slightly differently, that doesn't really matter. So the reality is they're in the same reference frame. So the star is stationary according to you. You're stationary according to Earth. You're measuring the distance between the Earth and the star. That will be proper length, a length measured by someone stationary relative to the start and end points. What's that, sorry? HD8 5512. Let's just call it HD8 for short. That has a bit of a ring to it. HD8. Yeah. Okay, so we've established that L0 is 36 light years. Now you can mess with units if you want, but the units end up cancelling out pretty easily, so we're just going to leave them as they are. You can convert that to meters, because light years is the speed of light times by a year, which you can then convert to seconds, and the seconds cancel out with the speed of light, meters per second, and you end up with just meters. So you can do that. We're not going to bother. We're going to leave it as light years because the units end up canceling out nice and easy. Now, I wonder if we should do that as an exercise, actually. Maybe we'll do that as an exercise one day, but we'll leave it for now. The question was not, is this proper length or relative length? The question was, calculate how many years it would take a spacecraft traveling at 0.98 c to reach that star from Earth if you were observing it from Earth. So we also know a velocity, 0.98 c. What are we being asked for there? For AI, you're going to have to be more specific. What are we being asked for? Time. What type of time? That question says find t of some sort. What t? Come on, guys. If you're on Earth, do you measure relative time or proper time? You measure relative time for a ship traveling across a distance. Can you take a clock and be present at both the starting and finishing events which you are measuring the time for? Are you there when the ship reaches the star? No. So who's measuring proper time? The person on the ship. You're measuring relative time. So we're going to say find t, not t naught. How do we find t? How do we find the time it takes if we know its speed and we know its distance? Yeah, velocity equals distance over time. Still works. It still works, it's just you're experiencing different distances in different times. But it still works, you still observe things correctly. So we can just do v equals d over t, or let's quickly rearrange for t. So t equals d over v. Is that right? V equals d over t. Yep. So it goes the opposite. Yep. Our distance in this case is L0, and our v is just v. And we get 36 light years divided by 0.98 c. Are we with me so far on this? Yes? Guys, do you need to split up? Getting very distracted by lots of different things. Lots to talk about, it seems like. And none of it is physics. Is this okay so far? Okay, so part II asks for the time taken for someone on the spacecraft. How are we going to do that? Oh, we should actually solve this, shouldn't we? 36 divided by 0.98 c. Can somebody do 36 divided by 0.98? This is where the units cancel out nice and neat. Remember that light years is the time, 1 year multiplied by the speed of light. What'd you get? 36.73 meters. Years. Sorry, years. So that is the relative time experienced. Is that fine so far? That's how long it would appear to take something traveling at that speed. Part 2. What have we been asked to find when they say that the observer is now on the spacecraft? Oh, why did I write I before, by the way? Now we're doing II. What are we being asked to find here? Mm-hmm. It would be surprisingly close. Yeah. It would be very close. The expansion of space should not actually change it. Yeah. Yeah. What am I being asked to find now? I'll ask again. Proper time, right? Now we want to find T0, proper time. Someone experiencing proper time on the ship. So, T equals T0 over square root of 1 minus B squared over C squared. All in brackets. And we get, oh, I cheated. I mean, I did it. Yeah, I was just going to give you the answer, but I should probably show you some of it. So we have to rearrange. So we end up doing, we're finding T0. We end up doing T0 equals T times by the Lorentz factor. Square root. It's kind of weird, but you actually don't here. That said, I would recommend you do as good practice. Convert it to seconds, in fact. But yeah, you can imagine the issues with that. So you can actually leave it as years because the only values in here, the only other units in here are from velocity. Now, if you did this calculation with velocity in meters per second, it wouldn't work. You would get the wrong answer. But this is C. This becomes just a number. So the units here, meters per second and meters per second, end up canceling out the units. And you end up with just the units of these two. So you can just use years and you'll get your answer in years. Does that make sense? Yeah, it's kind of weird, but it does save us a bit of effort. Best practice would be to go to SI units, but for this one sort of problem where you're given the speed and the speed of light, and you're given light years, it works. So it's 3 by 10 to the 8 is the speed of light every second, times by how many seconds there are in a year. So it's how far light travels in 1 year. Very far. 3 by 10 to the power of 8 by 60 to get minutes, by 60 to get hours, by 24 to get days, by 365 to get years. A lot, a big number, big old number.
Do we have a need to?
No. No, I mean, it's not that hard to work it out. You just plug it into a calculator, but I don't think it's going to come up. Okay, now you end up getting a proper time of 7.3 years. If you do all the math. How much? 9 trillion. 9.4 trillion kilometers. What's trillion? By 10 to the power of 11? But kilometers, so in meters, it'd be by 10 to the power of 14, maybe? 15? Yeah. Yeah, right. Do they do it in this question or something? Somewhere else? Okay, let's just pause and recap that, right? So first thing that's really important, velocity equals distance over time still works. It's just that the distances and the times are wonky. Because, remember, speed of light is the constant thing here. It's actually the speed of objects that stays consistent for everyone. If someone is moving 0.98 c relative to you, you are moving 0.98 c relative to them. Okay? We see different times and different senses of space, but we experience the same relative velocities. So velocity equals distance over time works perfectly well in an Einstein's relativity world. It's not a problem. You just have to make sure you use the right time and the right distance. Part B asks us to now calculate the distance traveled according to an observer on the spacecraft. What distance is that? The distance traveled, so we're talking about part B now. The distance traveled according to an observer on the spacecraft. Which distance is that? Do they measure proper length The person on the spacecraft measures proper length because they're stationary according to the start and end points? Are they? They're on a spacecraft moving from the start to the end. Would it look like the start and end were moving with them? When you run a 100-meter race, does it look like the end of the race is moving away from you at the same rate that you're moving? No, it comes towards you. The end is moving relative to you. You cannot measure proper length if the length is moving relative to you. So when you're on a ship traveling from Earth to a star, you can't measure proper length because the length you want to measure is moving relative to you. Remember, when you're on that ship, you don't experience that you're moving. Unless you're accelerating and changing your motion, you feel like you're just standing still with your ship. Your mug's on your table beside you, or maybe it's floating because you're in space, unless you have artificial gravity. Right? Everything is just sitting there, stationary around you, and it is the world rushing past. So, on a spacecraft, moving from Earth to a star, can you measure the proper length from Earth to the star? No. Measure relative length, because you see that thing moving relative to you. Okay. Okay, maybe we need to review this next lesson as well, because I feel like not much is going in at the moment. If you stop, yeah, so if you slow down to a point where the end goal seemed to be stationary and the point where you left seemed to be stationary, then you would measure proper length, as would a person on Earth, because both of you are now stationary relative to the length you are measuring. You're all in the same inertial reference frame. Okay, so B is saying find L. And I mean, the hint is we already know L0, so if you're asked for the other distance, you know it's going to be L. L is equal to L0. Remember length contraction? I mean, you can refer to your formula in data book, but it's just the inverse of time dilation, so it's multiplied by. L equals L0 times by the Lorentz factor. $36 times by one minus what will v squared, it was 0.9, c squared cancels, you get 0.98, so you end up with 0.02. $36 times by the square root of 0.02. $5.09. Oh, what units did we use there? Oh, no, that's fine. Yep. 5.09 light years. We should be back in. Because we used light years initially. Our units for length were light years. Did I do something wrong? So 1 minus, oh, right, sorry, 0.98 has to be squared first. 0.98 squared is 0.96, so 1 minus 0.9604, 1 minus 0.9604, right you are, I have made a mistake. Square root of that, and then that is times by 36. Sorry. And now I don't know what I need to write in here. 1 minus 0.98 squared. And then I'll just have calculated it from there. You end up with 7.16 light years. Okay, so a person on the spacecraft experiences relative length. They would observe the distance between Earth and the star, even if they were smack bang in the middle. If they measure forward and backwards, they would measure a length of 7.16 light years. Much, much smaller than the proper length measured by someone on Earth of 36 light years. Now remember, no one is right or wrong there. No correct answer here. They both are seeing what's real for them. Okay. Last thing I'll ask of you guys. Determine what the spacecraft occupants will calculate their speed to be from the results of AII and B. Remember, V equals D over T works for both parties here. They just have to use the correct lengths and the correct times. So the spacecraft observers relativistic length and proper time. What would they measure their velocity to be? I'm leaving that up to you. Part C, you are to do yourselves. I want to see it before you clock off for the afternoon and go home for naps.